For decades, automotive manufacturing was an exclusively physical domain. Quality control meant measuring mechanical tolerances on the assembly line. Even when computing first entered the vehicle interior, early digital dashboards and microcontrollers were isolated novelties. Today, a software-defined vehicle operates as a massive cyber-physical system. It relies on high-performance computing units to process machine learning algorithms and continuous data streams from external cloud infrastructure. Development teams push code through extreme continuous integration pipelines daily, while traditional auditors demand deterministic, milestone-based proofs that halt production. The lead auditor must move beyond the role of a post-development checker. The complexity of modern software requires the auditor to act as an integrated, model-centric process consultant. The modern audit relies on three pillars: API-driven model-based systems engineering, multi-standard co-engineering, and agile execution. Mastering these pillars allows the compliance process to keep pace with the technical reality of the vehicle. The first step is to stop accepting exported documents as definitive evidence. Auditors must mandate direct access to the system model as the single source of truth. This diagram shows the capabilities of the SysML version 2 standard. By introducing formal semantics and textual syntax, it bridges the gap between systems engineering and modern software repositories like Git. Instead of manually cross-referencing text requirements, auditors write API scripts to query the model for Metamodel rule violations directly. An automated script can scan the architecture and immediately flag orphaned requirements or unconnected ports that a human eye would miss. This API access allows for live testing of dynamic change impact analysis during the audit itself. Consider a specific scenario. Ask developers to relax an AI camera's latency constraint from 50 to 70 milliseconds. Then use API queries to track how that exact change ripples through the model and impacts the braking actuator's response time. Real-time API querying proves that an organization's traceability is a functioning engineering mechanism rather than a fabricated document. This diagram illustrates the complex compliance landscape for software-defined vehicles. They must satisfy functional safety, SOTIF, cybersecurity, and AI safety standards. The primary challenge is identifying architectural trade-offs where fulfilling one requirement covertly bypasses another's defense. Functional safety dictates strict hardware isolation and air gapping for high ASIL modules to prevent systemic faults. Yet cybersecurity requires open over-the-air pathways directly into those same modules for rapid zero-day vulnerability patching. The auditor resolves this by analyzing the system's namespaces. They verify that hypervisor sandboxing and memory isolation prevent incoming OTA patches from violating the physical execution timing of critical safety modules. Without integrated cross-domain architectural auditing, localized safety fixes inevitably create catastrophic systemic vulnerabilities. The ISO PAS 8800 standard addresses the inherent non-deterministic nature of AI and machine learning models. Auditors must stop demanding 100% proof of flawless execution from AI components. It is mathematically impossible and pressures teams to hide failures. The audit's objective must be reframed. The focus shifts to how the encompassing system detects an AI model's functional insufficiency and triggers its fail operational mechanisms. Take a real-world edge case. An AI team pushes an urgent neural net weight update through the CI/CD pipeline to correct a specific object recognition failure. The critical check is verifying the pipeline logs. The auditor ensures this urgent patch does not bypass the mandatory SOTIF hardware-in-the-loop simulations before deployment. True AI safety relies entirely on the rigidity of system-level fallback testing, not on the impossible perfection of individual model predictions. Even with API queries, disorganized data cannot prove system-level safety. Fragmented evidence is a liability. This diagram shows goal structuring notation, providing the definitive visual and logical framework for an integrated assurance case. The strategy node decomposes multi-standard requirements, while the context node strictly defines the operational design domain. The base of this structure rests on the solution nodes. These must never be vague text descriptions. Every GSN solution node must route directly to specific Git commits and SysML model artifacts via bidirectional hyperlinking. A mathematically sound GSN tree anchors every high-level safety claim directly to verifiable engineering data. It eliminates subjective auditor debates entirely. Attempting to run annual or milestone-based auditing schedules against daily software releases is a structural failure. Late-stage waterfall audits trigger massive, paralyzing rework within continuous deployment pipelines. The financial and operational costs are devastating. The solution is Agile auditing. This means reorganizing the audit team's workflow into integrated sprints that match the developer's exact rhythm. Auditors use Kanban boards to prioritize real-time business risks, like newly discovered zero-day vulnerabilities, pulling them ahead of rigid, pre-planned annual checklists. Integrating the auditor directly into the daily sprint cycle transforms their role. They are no longer an adversarial blocker, but a proactive enabler. This requires a cultural shift away from a punitive compliance mentality toward a framework of transparent, documented risk acceptance. Unresolved vulnerabilities must be handled constructively. They are logged as residual risks with explicit management sign-off, rather than hidden by developers who fear audit failure. Verification in the SDV era fundamentally relies on rapid real-time queries, dynamic system models, and relentless continuous integration. The lead auditor secures the autonomous age by anchoring every safety claim to the underlying engineering data.